Yeah, there you go. Okay, yeah. So Yoshi's wrong. Okay, how about Mario? In the middle, both the positive and negative charges will move. Right?
It's wrong. It's
wrong.
like only the negative moves, the positives stay where they are.
Okay, if the positives move, what does that mean?
It means that we change the form, like yours, like chemical reaction.
Exactly, absolutely. So positive charges don't move necessarily. Negative charges are free to move, though. Okay, so Mario is wrong. How about Bart? Someone else. Now I know your names, so I can just call on anyone. Shawnee, you want to try this one? Yeah, it's the same reason as what we said with Mario. It's false because positive charges don't move. So positive charges can't be pushed away if they can't move, right? Okay. And maybe everyone is wrong, so let's read the last one as well. If you put a positively charged rod near the wires, their free electrons will move towards the rod. Nicholas, you want to try that one?
It's right.
It's right? Okay. Is there...
Because the free electrons move on the wire.
Yeah, exactly. So it's electrons, so yes, they can move. It's on a wire, so it's a conductor, so they're free to move. Everything's okay. I would say that this person is right. I don't know who that character is. Anyone?
Brass. Yeah, brass. It's a doll.
Oh, I see. Okay, what's she called?
We don't know.
You don't know? She doesn't have a name? Okay. All right. Any questions about that? There's an animation. I don't want an animation. Okay. Okay, so here we have an electroscope, and it's a very simplified drawing of what you have here. I don't know if you guys can see it, but there are these two, it's written as two rectangles pointing downwards here, but those are the actual gold foils that when you apply these, if you bring this right close, these foils might separate or not separate depending on the situation. So that's what those two bars are. Okay, so let me ask you guys a question, is what would happen if I brought this this rod close to this electroscope? This is similar to what happened last time. Brahman. The gold leaves would separate, okay, so there would be a force in this direction and this direction. And, okay, go back. And what about the charges? Where would the charges be? Because I only drew the charges on the rod. You see the positive charges on the rod, but I didn't draw any of the charges on the electroscope. You want to add to it? Oh, no. Let me ask you guys a question. Bronwyn said negative charges go to the top. She's absolutely right about that. Where do I have to draw the positive charges for the electroscope? At the bottom? Okay, so there's definitely some at the bottom. That's what's causing the repulsion. Where else? Or is there anywhere else? Why is it doing that? Is there anywhere else? You want to try? In the copper wire, you mean the middle part? Yeah. We'll assume that they all went up, the electrons. The wire would be positive as well, okay. I agree. Exactly. All right, the positives are everywhere. I gotta fix this slide thing. Oh God, okay, give me 1 second again. Transitions, click on the mouse. So that should not change. Hopefully it's better now. Yeah, so there's positive charges everywhere because, nope, it's still not working. There's still positive charges everywhere because positive charges don't move, and every atom has protons, and therefore every atom has positive charges. Okay, so that's that. This is a little explanation to it. Now let's say I touched it, as you can see on the right here. Okay, my positively charged thing my positively charged rod touch the electroscope, what's going to happen in that situation? So help me draw the charges over here. What is it going to look like? Positive? It was positive on the left, and then you touched it, and now we're trying to figure out what it is. We don't know, I didn't draw anything. I'm not telling you if it's neutral or if it's charged, and I'm not telling you what the charge is if it's charged.
Well, some electrons are going to jump over
Okay, so the electrons from where jump from where to where?
from the
Yeah, absolutely. The electrons will jump into here, and therefore we're going to get some negative charges there. Okay, what else? Does a rod still have positive charges? Yes, absolutely. Does the electroscope have any more negative charges? No. Okay, so that would leave it like that. Yeah.
Why do you have the electroscope still positive since it's positive?
Originally it was neutral. So on the left it was neutral, right? So it's got positives and negatives. When the positive charged rod touches it, it's going to steal all the electrons. You're right, after a certain point it might steal them back because now that's positively charged and the rod is neutral. But we're assuming that the rod is very, very positive. Yeah.
I was just wondering, is it a matter of like volume? Let's say we have like a big like electroscope, like pretty big, and then we have like a tiny, tiny little valve. Like, would it be able to take all the electrons away, or is
It depends on how that rod was charged. Okay, that rod, we did it last time using the Van der Graaf machine. That's going to give it a huge positive charge. Not enough to be dangerous or anything like that, but still pretty big. And something that's neutral like that isn't going to give away. Something that small is not going to give all that many electrons. So we assume that the positively charged object is just very positive. Yeah. Yes?
For stated where there's an infinite amount of negative charges on the edge of the electroscope,
Okay.
and that the rod was like completely positive, then would it only take up a certain amount of electrons to become neutral, then it would stop?
Very good question. What do you guys think? So the question is, let's say the rod had 100 positive charges and the electroscope had an infinite number of electrons. How many electrons would the rod absorb? What do you think, Marco? 100. Yeah, because after that becomes neutral and there's no more electrostatic force. So remember, there has to be opposite charges for there to be a force between two objects. Okay, that was a good question. Anything else? What if I brought a negatively charged object to this electroscope? What's that? The electroscope is negative, and we're bringing it close to a neutral electroscope. What do you think?
It's going to try to discharge some of its electrons to try to be negative as neutral as possible.
It's not touching, so
Right now, most of the electrons are going to go towards the electroscope.
the electrons are going to go towards the electroscope. There can't be a transfer of electrons if there is no contact. Okay, so which side and which side?
So the going to be more negative on the side that's close to the electroscope.
Show me here. You think there is going to be
More electrons towards that part.
towards this part?
Yeah.
Okay, good observation. So Marco is saying that there might be electrons here because they're being pushed away from the rod. Bronwyn, what do you think? It would also go down because that's the furthest point. The electrons would go down, or we get pushed down. All right, and where are there positively charged parts on the electroscope? On the Top
top left side.
top left, there would be positives here. Everywhere. It's just that at the bottom, you have a lot more excess negative charges because they were pushed from the whole electroscope downwards. So if we had leaves here, would they be pushed away? Yes? Yeah, because two negative charges push away each other just similar like two positive charges do. So there would be the gold leaves pushed away and there would be electrostatic repulsion. Is that clear? Yeah.
So not all the negative charges
Well, because Marco was saying that it's just gonna, whatever happens, it's gonna be away from this, and he's right. So this is away from this, and this is also away from this. Okay, so it's just pushing them as far as away as it can go. So if it's being close to this side of the electroscope, maybe on this side there might be some negative charges. Yeah, Mark.
And the positives won't jump on the ball.
Positives don't move.
Yeah, that's it. So they will just stay there.
Exactly. Yeah. If there was contact, what would happen? Yeah, Maria.
The electrons will transfer and make the bond neutral.
Exactly. So the electrons would move if there was contact. So if contact, the electrons would move from the rod to the electroscope.
Until they have the same amount of electrons.
Yeah, until one of them becomes neutral. And one of them becomes neutral, there's no more force between them. Okay? Brahman?
But why would they jump if the electroscope is neutral?
Because it's pushing it away. The electrons push away the electrons, creating a local positively charged area. Yeah. We good with that? So last class, I told you guys that none of this matters if you don't find an application for it. Who here in their life has used an electroscope? You don't have one? Your parents didn't buy one? Of course not. No one used an electroscope. What I'm teaching you is just very theoretical. So you need to think of, why is this important? Here's something that's important. What is that? It's just a regular, very simple circuit, one resistor, one voltage source. Let's say this is 9 volts, and this is 2 ohms. Doesn't matter what those numbers are, right? Why? Oh, why? By the way, this is the positive terminal, the negative terminal. Why does a current travel through them? Who says that electric currents move, electrons move? What's the force that causes this current to start flowing? Yeah, the electrostatic force that we're learning. Look, there's a positive end and a negative end. Do these two ends touch here? What's the fastest way to get from here to here, or from here to here, rather? Is it to go that way or to go that way? Which way? What do you think?
Well, if it's a wire, then
Yeah.
the electrons tend to go through the wire.
Exactly. It has to go through the wire because here there is no contact, right? It's the same thing as here. No contact, right? So no transfer of electrons. So it has to go in the only way that it can go. And look, if this was neutral, if this terminal of the battery was neutral, would there be a current? No, it actually has to be positive and negative because this positive has to attract and convince the electrons to leave the negative end of the battery to come around and go into the positive end. You guys see what I'm saying? Okay. Application of why we're doing what we're doing right Okay. So we did this. There would be repulsion. We drew our arrows. Good. Next. Come on, guys. Come on. There we go. So here is an explanation of what you have, what we just did. It's written in words for you guys to have if you don't like the words that you wrote or if you don't like the words that I wrote. If you have any questions about that, you can ask me. I do feel like it's important that we talk about the difference between insulators and conductors. Who can tell me what those differences are in your terms, all right? I don't expect you to give me the scientific answer, but how do you understand insulators and conductors? I want to know that. Marco.
Well, a conductor is a substance that allows the proper transfer of electrons.
Okay. Conductor allows the proper transfer of electrons. So if I were to send electrons somewhere, I would use a conductor because a conductor might take my electrons and give them away more easily. What do you think?
I was going to say for the insulator.
What would you say?
Well, it's something that stops the flow of electrons.
To stop the flow of electrons? Like rubber? Okay. Okay, so that's how we understand them. Now, what's the physics, electricity, and magnetism definition of what a conductor and an insulator is? Let's start with conductor, because I think that one we know more about. So a conductor, what a conductor does is it has free moving electrons. Remember we were just talking about that when we were doing the 4 different responses from Mario, Yoshi, and those guys? So a conductor allows the free movement of electrons. And an insulator is basically just not that. It doesn't allow the free movement of electrons. Electrons are actually static. I want to show you guys an example.
Insulators can be charged.
They can be charged, yes, absolutely. Let me ask you something. Who was it that right, okay. So, if I rub this, Melanie, right? If I rub this on Melanie's hair, which part of it, okay, I would rub it like this. I'm not going to do it again because I messed up your hair last time. If I rub it like this, which part would you charge? This or the whole thing? Which part? The whole thing? Anyone have a different answer? I want you to explain it to me. Okay, so tell me why you think it's the whole thing.
Well, because at first it will be like an eye concentration over there, then it will like distribute evenly in the balloon.
Okay, so does someone agree or disagree with that statement? Based on what we talked about there. What do you think? Because are the electrons free to move? No, electrons are static. So when it comes to an insulator, I rub this part of it on Melanie's hair. That's the part that's going to be charged, and it's going to stay that charged in a perfect environment. Okay? So this part's going to be negatively charged, the rest of it is going to be neutral. Right? If I rub this on Melanie's hair, and let's say it did give you some kind of static electricity, it won't, but let's say it did. Let's say I rub this on Melanie's hair. Where would the electrons be? Here or all around? All around. If this is a conductive material, electrons are free to move. The electrons will repel each other because they're all negatively charged, and they'll try to be as evenly spaced out as possible. And the conductive material allows it, of course, to do that. Okay? So if I have a long wire, if I have a long wire, pretend it's a conductive wire, and I put an electron here, then I put another electron here, well, that electron is going to push the next one over. And that's going to push the next one over and over and over. And what am I going to get in the wire if I keep putting electrons here? Current. I have a current. If this was a rubber wire, or a rope, let's say, I put an electron there, and I put another electron there, are the electrons going to travel across? No, all right? Just because the electrons are not free to move, they're just going to be all localized here, and no current. That's why wires need to absolutely be in a metal or anything like this material. Thank you. Everyone understand that? Okay. Another thing that's really important to know is how can we charge objects? There's 3 ways. Who knows some of them? I don't expect anyone to know any of them, so I like guesses. I want to hear some guesses. Friction is definitely one of them. All right, that's number 1. Before I guess I move on to the other 2, why does friction cause a charge? What's that? Why do the electrons transfer when I rub them? If I just put this on my arm hair, why isn't my arm hair and the balloon getting charged? Why do I need to actually rub it? What's that? It's not an acceleration that generates a force. It's a force that generates acceleration, but that's not the reason why. What do you think? Oh, I thought you were going up for a hand raise. No? Someone? When you friction something, when you rub something, what kind of energy are we talking about? Mechanical energy, friction energy, heat energy, whatever you want to call it. You're generating some energy. Where does that energy go? Some of it goes into heat, yes. Yeah? Kinetic energy of the oxygen. Actually, what you're doing is you're exciting the electrons. The energy that you're giving it through friction, you're exciting the electrons. And the electrons are now going to be more motivated to go somewhere where they're happier. All right? And in the case, remember we had that triboelectric series? The list of all the materials there, and then where the positive goes. So it'll always go towards the one that it prefers. And in general, I can't tell you that it's always this case. In general, the electrons will go towards the substance that have the most electronegative atoms. Okay? You guys remember looking at a periodic table and grade 9 or 8 or whatever, and then they told you like, oh, all the ones on the right are electronegative and all the ones on the left are not electronegative. Do you guys remember that? All right, so this is important for that. All right, so this is something that has a lot of carbon. It's relatively right on the periodic table. It is therefore more electronegative and therefore more likely to get electrons when I rub it on my thing, which is made more of non-carbon compared to this. Okay, so friction because of the excitation of electrons. What's another one? How can I charge an object? Yeah.
Magnetic force.
Magnetic force doesn't change. No, magnetic force has to do with poles, which is different.
Well, I mean, like the wind generators.
Oh, I see what you mean.
With
That's.
copper coil and
You're right. What is the name of that? It's not magnetic force. It's not electromagnetism. I mean, that does do it, but that's not the general name of it. It starts with an I. It's the hardest one out of these 3. Induction. Let's do an example of induction. So if I were to turn this on, and this gets positively charged, what of the 3 different methods is used to charge this part of the ball? We talked about friction, it might be induction, and it might be this mystery 3rd one. Which one do you think it is? Why is this one getting charged? It's friction because of this belt, okay? The belt is moving up and down, causing there to be friction between 2 substances. Positive charges are going here, negative charges are escaping through the ground in the plug. All right, so now this is charged by friction. If I bring this close and not touch it, am I getting it through friction? Nope, I'm not touching it. There's no friction. Can't be. Is there a direct connection between this and this? Okay? There is, not if it's not touching, exactly. So it's not getting a direct connection. That's your hint for the mystery third one. So here's what's happening. If I bring this close, and then I bring it away, is this thing charged? No, it's neutral. If I were to bring it close, and then touch it, and then bring it away, then is it charged? Yes or no? Okay, let's try it. I mean, it's not going to work, but let's just pretend it's going to work because nothing with this Van de Graaff generator works for me. You guys have to tell me where the charges are going, okay? What's the charge on this thing? What's the charge on this thing? Okay, good. What's the charge on this thing? This thing. What's the charge on this thing? Well, over here it's going to be negative. Over here it's going to be positive. Overall, it's neutral. The negatives are up here, right? Can they go any further than that? They're being pushed away from this thing, right? Can they go any further away upwards? Sorry, the electron. The electrons. The electron. You're right. Sorry, I got mixed up. The electrons are here, and the proton or the positive charges are less negative up here. So this part is positively charged. We're good with that, right? If I how could I explain this? Let me not explain it and show you what I'm going to do now. I'm going to touch this. Okay? Everyone's okay? Ow. I wasn't expecting that. Okay? And then I'm going to remove my finger and move it here. So what happened when I touched it? Which part of this ball did I touch? Did the positive part or the negative part? Okay, so the positive part. So does this positive part have any attraction of anything? Does it attract anything? What does it attract? From where? From what does it have access to? It has access to my hand, so it's going to withdraw my electrons and into here, all right? Did it still have those electrons it started off with? Yeah, because I never touched it. It never lost it to the electroscope, assuming that big shock didn't happen. So now when I took it away, the electrons that were localized here are now everywhere again, and it's holding my electrons. So is it charged or not? What's the charge of it? Negative. It's negative. You guys understand that? That's what induction is. Okay? So you get it through being partially charged on two different ends. Okay? Let's write that down. Try to write that down in your words, and I'll try to not be too scientific about it. I have a follow-up question because I want you guys to think about this. Excitation of electrons, induction. So this is the polarized object. A polarized object getting charged through a ground. So, yeah, I just want to explain a little bit my wording. I said a polarized object. Here, this was my polarized object. You guys told me that the negative charges were at the bottom, the positive charges were at the top, right? So that's polarized. The positive and the negative charges are on two different poles of this object. And then I'm the ground because I am giving it relief through my excess electrons, or I'm taking its excess electrons if it has excess electrons. All right? You guys understand what I'm saying? Okay. Let me ask you guys a follow-up question. I'll give you 2 minutes to write it down. Yeah, Brian?
Is induction like a process of when your finger touches the ball, or is it just a process of
So it's how to charge an object. So this became negatively charged because we induced a negatively charged part to it. That's,
like the whole process?
yeah, it's the whole process to make this object charged. Let me ask you guys to follow. Where's the writing? All right, so let's follow again what's happening. It's a good exercise to do this. This is
Positive.
positive, okay, very good. I'm going to bring this close. What is this thing now? Is it neutral? It's still neutral but polarized, all right? I want to touch it. Oh, jeez. Hurts every time. If I touch it, all right, and here's what I'm going to do. I'm going to remove it, and then I'm going to let go. What is this? What do you think, Marco? It's neutral. Why did you say that?
Because there's no more all the electrons that were stuck at the bottom, they went back up, and they repelled the electrons that were there from your hand to the rod, so those electrons went back.
Yeah, that's correct. Does someone have another way of saying it? That's correct. Essentially, I took back my electrons, okay? Because there was nothing pulling those electrons from this anymore, now I'm the thing that's positively charged, so I'm going to take my electrons back from this. This thing's going to be neutral. So the only way for it to work is if I touched it and then moved it, okay? That's how I charge this by induction. All right, what's the third way? We've kind of alluded to it. If you were to, yeah, Rowan?
Like touching the charge
Yeah, and what's the name that we give to that?
conduction.
Conduction. Oh, come on. Being, every time I put a dot, it skips to the next slide. I gotta stop putting dots. Being connected to a source. If you put your finger in an outlet, I mean, let's say your fingers are slim enough to fit in an outlet, would you get charged?
Are you going to show us how you
Sure, you know, let's just do it. Yeah, you get charged, right? If you put your fingers in an electric socket, you're going to get charged. It's not going to be pleasant, but you'll get charged. The way your device gets charged is you plug it into an outlet and you have access to a source, a direct connection to a source, and you get charged through that way. Okay? So these are the 3 ways that you could you can create a charged object, right? So that's it for this part. All right, we're going to take a 5-minute break. So come back at 10:21, and we're going to start the next part of this. It's on the same subject, but now we're going to quantify our measurements, okay? So come back at 10:21. Yeah. You want to come and show me? See, that's what when I was talking to the other guys, it's not the answer. I was like, your students are right. It's kind of confusing. How would you explain it? And they said it's not really possible to tell because they cut the videos. And when you cut the video, you don't know. So they rub it, and then they cut it, and then the next time you see it, there's two plates that are. So we don't know if they rub both. We don't know if
But like if you rub both, like they can make some force in that case. If you were to put in that case, you become positive, you become the negative choice when they test it.
right. If you're, because the person's hand was in contact with the top plate, right? So it's possible that the plate removes some charges from you because it's positively charged from the friction.
Holding on to your hand and not to
Exactly. So if the plate was positive and it drew some of your negative charges, you're positive. So you should theoretically be repelling the plate, but that wasn't the case. So now the teachers and I would thought maybe they also rub the plate, which would make a difference, and then it would be an attraction. So it's just not possible.
So like anything that kind of is like I think you know how to turn the and you have to force from the opposite depending like no matter
Yeah, so
what it is.
if you have a charged object, right, you can charge this and make it positive by conduction, or I could use the positive charge to make it negative by induction. You see what I mean? So in both cases, I use the positively charged thing. But in one case, I got a positively charged rod, and in the other case, I got a negatively charged rod. It's possible to do both.
But anything that you broke, like in the individual, there's also like you
Yeah. No, not necessarily. So remember last class I showed you guys this triboelectric series? I'll show you. You guys are group 3. Any second. There we go. Remember this list here? Remember this?
Yeah.
Okay, so this will tell you what's going to become, when you do friction, what's going to become what. Okay, so in that case it was wool and PVC. So the pipe was made up of PVC, which is here, and wool is up here. So the wool is going to become positive because it's closer to the positive end, and the PVC is going to become negative.
So then it was like holding on, like it was contracting the can. So a can, like a Coke can. That means the can is positive.
Not necessarily. So now what you're doing is you're bringing this negatively charged PVC vinyl pipe, right, next to a can that's uncharged, it's neutral, right? And what you're going to do is you're going to separate the charges. And because you're separating the charges, there's going to be a force of attraction. And it's going to roll forward to try to get closer to the rod. And if it rolls, then the new part of the can is going to be positively charged. So it's going to keep rolling and rolling. You got what I'm trying to say? So I bring this close to here, so all the positive charge is going to try to run away. Or not run away, but use the positive charge. So now there is an attraction between these two. Exactly. So now we're going to roll. It's going to try to come forward, come and attach to this attraction. So it's going to roll in this direction. Right? And now it's rotated. Now you have the can is in a different position, which before it was being attracted to here. Now this is the closest part. So now the new part is going to be attracted. So it's going to roll again. Try to get close.
And like,
The homemade electroscope?
yeah, and they were
Okay.
using like a PVC pipe, but sometimes they would come close to it and they would like separate. But then sometimes they would stay together and get close to the pipe, so it was confusing. But like they were using the same pipe, and sometimes they would follow the pipe, and sometimes it just wouldn't. Even when they would, like sometimes when they rubbed the pipe, when they touched the pipe against
Oh, you're
the,
talking about the matchstick, not the electroscope. The one that has a little stick hanging from it? I have it here if you want it. Let's just manually look for it.
oh, so I have it here.
You got it? This one, right?
Yeah. Like they're not touching right now. Like they touch and they don't.
Essentially, it's what we talked about.
But like then she rubs it and then she tries to touch the pipe against the thing.
I think what you're noticing is that they're loose on the hook, so they just keep falling back because of gravity. It's the same situation as this. Okay, let's move on to the second part. So please open up the third PowerPoint. All right. So now we're going to deal with Coulomb's law, which is exactly what we've been doing this whole time, but now we're just giving it a name. It's still the attraction, the force of attraction between two oppositely charged particles, or the repulsion between two similarly charged particles. And Coulomb's law is the formula you use to calculate that. Okay. Let me just move this electroscope. Right. So we're going to be able to apply Coulomb's law today. And this is what it is. Okay, that's the equation for it. What do you think these variables mean? I want you guys to try and guess it. What do you think, Melanie? Yeah, constant. Yeah.
How much Q1 and Q2 are like both the objects
Okay.
that we're dealing with?
Exactly. So because the attraction or the repulsion occurs between two objects, so that has to describe the two objects. Which part of the two objects? Which aspect of the two objects? Marco, what do you think?
It's the charge.
Exactly.
The R is called.
Very good. Charge of the two objects. What's that? Ah, okay. That wasn't supposed to show up. It's this damn touching thing. Okay, and then a distance. Now, the constant here is 8.99 times 10 to the 9. I tend to just think of it as 9 times 10 to the 9. I'm okay if you guys do that too. So 9 times, if you want to round it to 9 times 10 to the 9. And an easy way to remember it is if you remember that on your calculator, you have to type in 9E9, so like 9E9, get it? Anyway, easy way to remember it. Yeah?
Do you like consider significant figures?
Yes.
All right.
Yeah, but when we consider significant figures, do we consider constants? No, constants aren't a measured value, so therefore we don't calculate them in our in our significance. All right. But yes, every time you guys have a test, an assignment, or a lab, you have to use significant figures. Good question. This is similar to this formula, which is what? Nadia? Yeah. Yeah, exactly. So what's the name of this one? It is a force of attraction, but what's its actual name? Yeah, it's a universal gravitational force. I don't know why it's so laggy. My computer's trying to do too many things at once. Let's draw some parallels by talking about the universal law of gravitation and Coulomb's law. We have our equations. I'm just going to rewrite them here. I want you to do the same thing, please. We're going to call the electrostatic force Fe, okay, just because we need to give it a subscript. So we have Fg for the force of gravity, Ft for the tension force, Fn for the normal force. We're going to give Fe for the electrostatic force, okay? So very similar. And each of them have their own constants. There is a universal gravitational constant, G, for gravity. And there is the dielectric constant, K, for electrostatic force. And so we're just going to give these names. This is gravitational force. And this one is going to be electrostatic force. All right. I want you guys to help me for this last one, except for you, Mark, because you have yesterday's slide open. You're group 3. So when you go on Moodle, make sure you pick group 3. That's because it's a third PowerPoint, but it's students 02. Okay. So when we're talking about the force of attraction between two objects in terms of gravity, what do these two objects have to have for this attraction to be possible? So I'm at gravity, right? So these two things have to have a mass, exactly. In electrostatic force, the two objects in question need to have a charge. Yeah, that's the difference, right? These are the conditions of the use. So objects need to have a mass for gravity, and objects need to have a charge for electrostatics. Any questions? I want you guys to have this slide here because you're going to need to use the what do you call it? You're going to need to use these numbers when you do calculation. The one that's important for you right now is this constant k. Just keep that in mind, is 9E9. And this formula, today we're going to be using this formula a lot. Okay? So we have a problem. We're going to solve this problem together. Although, I just realized I don't have enough space here. So let me just make myself another slide. Keep doing. Excellent. All right, so here we have 3 charged particles. Okay, each of them have a quantified charge. Remember yesterday we were talking about coulombs? Last class we talked about coulombs and how many charges are in a coulomb. Well, we can measure charges in coulombs, and that's what this is. What does this symbol mean again? -6 or 6? -6. -6. Also, you can also say it's microcoulombs. And here we have a distance, so we know that this is kind of like an equilateral triangle, right? If we know an equilateral triangle. So, it's not drawn to scale because the projector is actually squishing the screen a little bit. I'm asking you, if I put these 3 charged particles on each end of this equilateral triangle, I want to know what the force is acting on Q3. Okay? So what we need to do is figure out which force Q1 is providing it and which force Q2 is providing it. So Q1, you can see, is +4 microcoulombs, and Q3 is -6 microcoulombs. First and foremost, are they going to attract or repel? They're going to attract, absolutely. Okay, so if they're going to attract, you can draw a vector force in that direction because it's Q3 is being pulled into Q1. All right. Now if we take a look at Q2, Q2 is negative and Q3 is negative. Is it going to be a force of attraction, or repulsion? Repulsion, absolutely. So we can draw another force. So this is Fe. This one was Fe from Q1. This one's going to be Fe from Q2. So the resulting force is what? What is the total force that Q3 feels? If I were to push Mark and Nicholas were to push Mark and we're pushing them in that direction, which way is Mark going to go? So if I push him, you push him, right? Kind of at an angle. He's going to go in that direction. So how did his new direction get determined? The net force. Okay, perfect. So now we have a vector system. We have all the angles that we need. This one is 60 degrees, right? And we can decide that this is going to be our frame of reference, right? We have our y direction and our x direction. Our resulting force is going to be somewhere in the middle of those two, correct? So we're expecting something that looks maybe like this for F net. All right, excuse my crappy handwriting. I don't often write on screens. Yeah, so that's F net. And F net, you expect F net to have a positive x and a positive y direction. All right, that's how you know we will have done this more or less correctly. Let's go and do these calculations. All right, so we're going to draw a free body diagram. We always draw a free body diagram. We're going to call this FE1. We're going to call this one FE2. All right, and so the F total, or F net rather, is going to be equal to F1 or FE1 plus FE2. We can't just add them up like that, can we? Why can't we just not add them up? Exactly, they're not going in the same direction. So I can't just calculate FE1 and plug it into that, and then calculate FE2 and plug it into that to find F net. All right, so I have to separate them into x and y axis. So that's what I'll do here. I have an x, I have a y. This is how I do it. If you have a different method, by all means, use your different method. I can tell you, though, that my method is the best method ever made to human existence. Okay? So Fe1 is a force of attraction. I don't care if it's negative or positive, right? If I were to describe Fe1, right? If I were to describe Fe1, what is the y direction? Is it positive or negative? It's positive because it's going upwards. Is it, and the x direction, is it positive or negative? Negative because it's going the negative x direction. Remember, I established what my directions were. What about for my Fe2 in the x direction, positive or negative? In the y direction? 0, exactly. So I should automatically, for Fe2, have a 0 there. All right, and I'm going to have to somehow solve for these three here. Okay, Fe2 is easy because all of the force that it's feeling from Q2 is in the x direction. So I can say that Fe2 is equal to, oh, it's going to annoy me, KQ1, nope, not Q1, Q2, Q3 over R squared. And that's easy because I have a number for all of those. So 9E9 times Q2, which was negative 8 times 10 to the negative 6 coulombs, times Q3, which was negative 6 times 10 to the negative 6 coulombs. All this over 1.2 meters squared. Okay. So who can give me an answer for Fe2? I don't have my calculator, or I do, it's just the battery's dead. It's a weird number. 0.3. Is that what everyone got? Everyone's in agreement with 0.3? What are the units? Can I ask you guys one favor? When you show your work on your tests, I don't care what you do on your notes right now, but when you show your work on your tests, on your exams, on your labs, always write the units when you can. Okay? In the equation, here I wrote coulombs, meters. I didn't write the one for this because it's really long and complicated and there's not enough space here, but you should write it, okay? Everything should have units. That's a way for you to make sure that you've made all the right steps. You didn't make any stupid calculations. The units should cancel out. My answer should be in newtons. So, I mean, there's newtons in the constant units, and this should cancel out and leave you only just newtons behind. All right. How do we calculate Fe1? Well, let's calculate Fe1. You guys do that. It's going to be KQ1 Q3 over R squared. All right, I'm not going to enter the numbers here, but you guys calculate it, please. Give me a number, and then we'll figure out what we need to put in the tables. Did you get a number? Negative number? But we know something, right? We know the direction it's supposed to go in. So we don't really care about the sign right now. What number did you get? What did you get? 0.15? Does everyone get that? 0.15 what? Newtons. Please, 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 please don't forget those units, all right? So if it's 0.15 newtons, is it 0.15 newtons in the x direction, in the y direction, or do we need to break it up? We need to break it up. Now, if you notice over here, in the top left, we have an idea of where it goes. So look, there is a 60-degree angle there, all right? This is a 60-degree angle. We have the hypotenuse. We can figure out the x, which is going to be negative, and we can figure out the y, which is going to be positive. So break them up. Use your trigonometry, SOHCAHTOA. You guys remember that rule? Did you also learn SOHCAHTOA, or is that just me? Yeah, okay, perfect. Use it, and tell me what the values are going to be for x and y. Does someone have an answer for x? What did you get, Melanie? 0.075? Newtons? Please say the units. Positive or negative? Negative, very good. Someone get something for y? Anyone? Why? What did I get? 0.13 Newton. Positive or negative? Okay, so now we can enter them here. 0.13 newtons and negative 0.075 newtons. This pen is weird, eh? 0.075. All right, now we can find our total force. We just have to add up everything in the x column, add up everything in the y column. And the y column is easy, 0.13 newtons. And the x column is 0.0225. 0.225, right? If I were to take into account my significant figures, what should this number be here? 0.2, okay? Because it's an addition rule, so you have to follow that. I'm choosing to ignore it just because I want to keep as many as possible. Yeah, Shani?
I just started to, I did it, it was
Minus 0.13? Ah, okay, because you used the signs in Q1 and Q2, but you know, you're talking about, because what was Q1? What was Q1 that was here? What was the charge for it? And what was the charge for Q3? Negative. So when you multiply a positive and a negative number, you got a negative number, right? But that's just telling you that there is an attraction, all right? But what you need to remember is that it's going in the positive direction, okay? Exactly. You have to use your free body diagram to determine. Okay? So let's say you determine that this is a number. You know that it's going in the positive direction, so you know that it's going to be positive. Because remember, we decided that that's the positive x direction. And that's the positive y direction. That's the positive x direction. That's the positive y direction.
Yeah, that was my question.
What's that?
You put the minus instead of the 0.15 for the x, but not for the y. Does that actually change the answer?
Here? I did that because this is for FE1, and FE1, in the x direction it's negative, and the y direction is positive. So I put it negative there because I know in the x direction is negative, and I didn't put it here because I know in the y direction it's positive.
So that changes the answer, right?
Yeah.
Then it's 0.15 times 76 is 0.13, 0.17.
If I put a negative there or not, the only thing that it should change is whether or not this answer is negative.
Really?
Yeah. Maybe you're not putting brackets around your sine 60. And make sure also everyone's in degree mode, eh? Okay, so now once I have this x and y, what do I do with it? I have this. What do I do with this? Because that's not what my answer is. My answer is, what is the force acting on Q3? What do I do with it? Mark.
I just had a blank. Oh, yeah, like, you could do like a Pythagorean rule.
Yeah.
Where you like square both and then you find the hypotenuse.
Exactly. So you have the x side of the right angle triangle. You have the y side of the right angle triangle. You can use Pythagorean theorem or Pythagoras to figure out what your hypotenuse is. So just x squared plus y squared, square root of the whole thing. That'll give you the magnitude of the force that's acting on Q3. So then F net is equal to the square root of F net x squared plus F net y squared. Then I'll take an answer if you guys have it. Brown? 0.26? Does everyone get that? Newtons? Yep. And how did you get the angle? You can do it using the sine law. Oh yeah, you can use the sine law, yeah. There is a more simple way to do it.
Tangent.
Yeah, you can do inverse tangent of the x and the y. Okay. So what did you get, Brown? 30 degrees. Very good. Okay. I believe your next slide is blank. Could you go to the next slide, Nicholas, so I can see what you have? It's blank? Okay, it's because I added stuff to it afterwards. So here is your next problem. I want you guys to work on this on your own, and we're going to correct it in a few minutes, okay? It should be relatively straightforward. What I want you guys to remember, though, from mechanics, because we're doing some mechanics now, is that friction is a product of the coefficient of friction and the normal force, okay? That's what you need to remember for this problem. But you know mechanics, right? Just fair warning about this question. I didn't think about it too much. The answer is humongous. So if you're sitting next to people, you can work with them. Try to do this together. All right? If you want to work on it alone, it's also up to you. But it's good to work in groups. Discuss it. Ask questions. Yeah, the distance is 1 meter. That's it. S, that's the coefficient of T. What's that? It's mu, it's the Greek letter mu. It's, well, it depends if it's on a flat surface or not. But its force of friction is equal to the coefficient of static friction in this case, times normal force. And if the normal force, if the object's on a flat surface,
Yeah, it's the
the
mass
normal
times the
force
gravity.
is the mass times gravity. Yeah. Million. Like millimeters.
Oh.
Yeah. Yeah. Like millimeters and millimeters. If you're having a hard time, always start by drawing a free body diagram. It is the best way of doing it. It is huge. The answer is huge. What did you get? If you're done, move on to the next problem.